So, Beef, what do you think of that lesson today in class?
I didn't really get it, you know, Simpson's rule, it's kind of tough.
I was pretty confused. You think we should go maybe work some out in the classroom?
Right? It's a great idea.
See if we can get some.
Yeah.
Oh, God damn, it's locked.
Dang nabbit.
Oh, God.
Let's go check some information on the computer.
Yeah, let's do it.
Well, you look at that, Beef.
It's already open. Oh my God.
Oh, it is our lucky day. Simpson's rule. It says here, this method is credited to the mathematician Thomas Simpson, not the door,
Not the door.
He's not a hockey player, of England. And it says that Kelp used similar formulas over 100 years prior. Wow. Fascinating.
It also says here that sort of like Riemann sums. Oh, we did that earlier in the year. Should be pretty simple then.
Not too bad. What do you say we go work some out in the classroom?
I heard Professor Nelms is having a little review session downstairs.
Let's go!
Great idea.
How's it going, class? My name is Professor Nelms, and today we're going to be talking about Simpson's rule. Now, what is Simpson's rule, you might ask? Well, Simpson's rule is what we use to approximate the value of a definite integral. What's cool about Simpson's rule is that it gives you exact results of the function as opposed to Riemann sums, which are more of an estimate. So that's what differentiates Simpson's rule from Riemann sums. So, what Simpson's rule basically states is that when we have a function over the interval of a to b, we use this formula down here, which starts out as delta x over 3. And we see here that delta x is equal to the length of the interval, or b minus a over n, which is the number of intervals that we're going to use, because like we said earlier, the more intervals that we use in approximating the value of a definite integral, the more exact results we're going to get. And so the problem will give you the number of intervals that you're going to use, and so what you then do is you plug it in with the length of the interval in order to find delta x, which is basically going to help give you the length. Well, it's not going to help. It's going to give you the length of in between each interval that we use. And so, but we need to make sure that n must be even. So the problem's going to give you the value of n, but it must be even in order for Simpson's rule to work properly. So, going back to the problem, we solve for delta x, divide that by 3, and then we multiply. What we do here is we determine the value of the function at each subset. So at x subset 0, because we're going to have a bunch of intervals, so at each interval we approximate the value of whatever the function is. But what we do is we put to start for the first and the last coefficients, we put 1. And then in between, for each of the intervals in between the first and the last interval, we rotate 4 and 2 in the coefficients, because that helps to approximate the value. It's basically the whole point behind Simpson's rule is it goes along the line of the function so that you can get all of the area. And so you start with 1 in the coefficient, you evaluate the function at x subset 0, and then you multiply, or you don't multiply, you put 4 and 2 as the coefficients for the next intervals, alternate them, and then the last coefficient you do 1 for the last interval. So, and then you multiply that all together, and that should give you basically what the fn function would give you in your calculator if you were doing it in your calculator. So I know this sounds confusing to you, but hopefully a sample problem will be able to solve things and make it more clear. Here's our sample problem over the interval of from 0 to 3 of this function, 1 over 1 plus x to the 5th dx, with your n as equal to 6. And this is all part of the original equation. We haven't done any math just yet. So what we need to do first, because we know that this is the equation that we need to match, so we need delta x. And remember, we said delta x is equal to the length of the interval, or b minus a over n, which is given to us. So to go back here, b minus a would be 3 minus 0. So we can write that in here, over n, which is the length, or which is the number of intervals that we're going to use, right here, which is equivalent to 1/2. So once we have 1/2, we know the distance between the intervals that we're going to use, and I've already written them down here. So we know we're going from 0 to 3 as stated in the original problem, and so we're going to make our interval marks at 1/2, 1, 3/2, 2, 5/2, and 3. So we have 6 intervals, because remember, n, the number of intervals, is 6. And I've marked them down here as x subset 0, x subset 1, 2, 3, 4, all the way to 6. And so now we're ready to begin the problem. So what we're going to do is we're going to start with delta x over 3 like we had in our our example. So delta x we said is equal to 1/2 over 3, which is also 1/6. So we can go ahead and change that up there. 1/6. So first what we're going to do is, because remember our leading coefficient for the first subset is always going to be 1, as is our last coefficient. And then in between the coefficients are going to alternate 4, 2, 4, 2 for each of the subsets we're going to be using. So to start, we're going to go 1 times f of x subset 0. So what we're going to do is we look at subset 0 and we see that the value is 0. So we're going to plug in here 1 over 1 plus 0 to the 5th, because that's x subset 0. And then when we do this out, we see that the answer is just 1 over 1. But we're going to get to that later. We're just going to write everything out first, and then we're going to go ahead and calculate it all. And so then we continue on. We add 4. So we start with this 4 coefficient here, and then we're going to start with the pattern of 4, 2, 4, 2. And then we go f of x subset 1. And we look and see subset 1 is equal to the value of 1/2. So we go 1 over 1 plus 1/2 to the 5th. Because we plugged in the subset value here. And then we continue on, plus 2, because remember we're alternating 4 and 2, of f of x subset 2. We look at subset 2 and see that the value for subset 2 is 1. And then we go ahead and plug 1 into the original equation here. 1 over 1 plus 1 to the 5th. And then we go back to 4 because we're using the alternating coefficient pattern. And we continue on with x subset 3, which is equal to 3/2. So then we plug in 3/2 here into the original equation. 1 plus 3/2 to the 5th. And then we'll come down here. So next up is x subset 4 with the coefficient pattern of 2, or with the coefficient of 2, sorry. So we add plus 2. X subset 4 we see is 2, and we plug it into the original equation. 1 plus 1, 1 over 1 plus 2 to the 5th. And then we go back to 4 again, with x subset 5 this time, which is 5/2. So we plug in 1 plus 1 over 1 plus 5/2 to the 5th. And then for the last coefficient, remember as we said we were going to start with 1 and we're going to end with 1 here. So we put 1 as the coefficient and we plug in x subset 6, which is equal to 3, which is 1 over 1 plus 3 raised to the 5th. Alright, so it's a very tedious problem. I wouldn't say Simpson's rule is very challenging in terms of the calculus, but it's more just very tedious, repetitive problem. So we're going to go ahead and solve this. Alright, so after calculating out this problem, and remembering to multiply by 1/6, because that's what we had for delta x over 3 at the very beginning here, we've come to the approximate value of 1.074915. And when we use the fnint function in the calculator to get the exact value of the definite integral, we get 1.0659. So fnint equals 1.0659, and Simpson's rule equals 1.074, which is very similar. That's less than 0.5% off. So that's That's unbelievable there. And that's why we use Simpson's rule to approximate as close to the exact value as we can get of a definite integral. So I hope this extra help session has helped you out a lot. And good luck in your exams, good luck with the rest of the term, and take care.